In the last video, I introduced the mixture of Gaussians model. And before moving on to talk about learning and inference, what I want to do first is just take a little bit longer to consider that model, because I often get questions about it and about precisely what the role of each one of the parameters in that model is. We'll also talk a little bit more in detail about why it's called a mixture of Gaussians model. And I want to do that through asking you a question. The question is going to focus on a really simple case where we can visualize things easily. And so I'm going to imagine the dimensionality of our observed data in this case is just 1. Remember, this is the dimensionality of our observed variables xn. So we're looking at 1D mixtures of Gaussians. And I'm going to specify a model in that case with k equals to 3 components. Okay, so our underlying variable s can take one of 3 different variables. It can be either Sn is equal to 1, Sn is equal to 2, or Sn is equal to 3, corresponding to 3 different clusters. So in the model that I'm interested in, the mixing proportions, that's the name given to these pies here, are going to have the following 3 values. The probability a priori of coming from cluster 1 is 1/4, probability of coming from cluster 2 is 1/2, and the probability of coming from cluster 3 is 1/4. The means of these 3 components are going to be 0, 3, and -3. And the standard deviations, in this case, the covariance matrices collapse back to standard deviations because it's just a scalar case, are going to be 1/2, 1/2, and 1. And what I want you to do is to go away and think about how or which one of the plots below shows you p of x given theta. So below are 3 different density plots over x. One of them is the correct match to the generative model above, and the other 2 are incorrect. And just to remind you, I've specified, the probabilistic description of the mixture of Gaussians at the model at the bottom. So if you could pause the video, try and work that out for 30 seconds, and then we'll sort of run through the solution. Great. Well, I hope you attempted that solution. So first off, before we sort of talk about the correspondence, I just wanted to run through a little bit of algebra that connects the equations at the bottom here. So the description of the model in terms of p of s and p of x given s to the actual distributions which are plotted in the 3 subplots here. So in a bit more detail, I want to show you how to calculate p of x given theta from the model description. And the way to do that is to use the sum rule. So we know that p of x given theta is equal to p of s given theta times p of x given s and theta, marginalizing out over all possible settings of the variable s. This is the sum rule of probability. So just notice, for the sake of generality, that this thing written in here is nothing other than the joint over s and x. I've actually been a bit sneaky here. It's the sum rule plus the chain rule, the product rule, I've used together. So this is the way to form the marginal distribution p of x given theta, given the specification for the model. We can now substitute these 2 into here. This one gets substituted into here, and this expression gets substituted into here, and we get the following expression for p of x given theta is equal to pi k, that's just p of s given theta, times the Gaussian in x with a mean mu k and a variance sigma k squared. Okay, so just apply the sum of the product rules and we end up being able to connect p of x given theta to the quantities in the model. So let's just eyeball this equation for a little bit. It says that the distribution over x specified by a generative model just looks like a sum of weighted Gaussians. So each of the Gaussian gets multiplied by a pi k, and then is a Gaussian with mean mu k and variance sigma k squared. And for this reason, it's called the mixture of Gaussians model, because it contains a linear combination of Gaussians where the weight on each one of those Gaussians is just a pi k. So we expect to see 3 Gaussians with different weights attached to them. And broadly speaking, A, B, and C each look like a mixture of Gaussians. In fact, they are mixtures of Gaussians, but the mixture components are slightly off. So the relative heights are slightly off, the widths are slightly off. And so we have to figure out which one corresponds to the settings at the top. Okay, so let's do that. So the first thing we're going to look at, let's take these things component by component. Let's look at the first component here. So the first component should have a mean at 0, a variance of a half, which is the narrowest variance, and an a priori mixing coefficient of a quarter. The pi k is equal to a quarter. So the components we're looking at will all be at 0. Okay. So one of these 3 has got to be the appropriate one. This one looks a bit broad. Okay. This one looks a bit broad because the variance in here is the smallest of the 3 variances. It's equally small as compared to component 2. So probably this one we're thinking probably isn't the right picture. But at the moment it's hard to tell which of these 2 is the right picture, although we might suspect it's this one because the height of this Gaussian is relatively small and the pi up here is a quarter. So which is the smallest of the 3 pi's. Pi 2 is a bit bigger than it. So we might expect it to have more weight, the next component that we're going to consider next. It's not completely trivial to see, just by looking at the heights of the Gaussians, what the relative pi's are, because it's confounded by the widths. If a Gaussian has a narrower width, it has a higher density at 0. So it's a little bit tricky to eyeball them and be exactly sure, just based on the heights, what the setting of pi is for each one of the, in each one of the 3 pictures. So let's look at the second component now and see whether that rules some things in and out. So here is second component. That has there's a big chance a priori we come from that cluster. So it will have high mass. It's situated at a mean of equal to 3. So it's going to be the one out here. Okay, positive 3. This is the one we're looking at. And it has a narrow variance. It's as narrow as the first one. So now we're, on surer ground, having considered this one, because we know the widths of the 2 must be the same. That definitely rules out this one, because these 2 widths look different from one another. We've got one broad one and one skinny one. Let's look at the relative weight. Well, compared to cluster 1, the weight should be equal to a half. And so we'd expect to see the Gaussian at 0 to be smaller than the one at 3 here. And that's indeed the case for this one. Is not the case for this one. So that pretty much rules this one out. And then we can do a quick check by looking at the last component to make sure that B is indeed compatible with this model. We've got a quarter, minus 3, and 1. So this one is a broader Gaussian than those previously considered, and indeed that does just check out, and it has a relatively low weight, so we'd expect it to be smaller than this one due to the smaller variance, or the larger variance, so that the component at minus 3 has. So this is minus 3 down here. So B is indeed the correct answer, and here you can see that I've actually plotted out the components below, and I've coloured them so you can see the underlying Gaussians which make up this mixture of Gaussians model. Great, so if you're happy with that, I think you've got a good grasp of the mixture of Gaussians model. It'll turn out that this calculation, when we marginalized out the latent variable to get this density over P of x given theta, that's going to be key for learning, and we'll use that calculation again in the next video.